So we've been looking at the solution to systems of equations, which in 3 dimensions is the same as saying, where do 3 planes intersect? Or 2 planes. All right, but before we do that, I want to go into something called row-reduced echelon form of the matrix. So yesterday, we went to this reduced echelon form of the matrix, where we have this nice little triangle of zeros here, and we can directly read from this reduced echelon form that Z is equal to 3. And so in the solution to this system of equations with planes, the point of intersection of these planes happens when Z is equal to 3. And yesterday, we took that value of Z and we substituted it back into the second equation, or the equation in this row, number 2. Found out what the value of Y was, and then we took the value of Z and Y, substituted it back into row number 1 to find the value of X, okay? And once again, matrix, it's just representing a system of equations. You just have to remember which thing is X, Y, and Z. And it saves you all that extra work of writing down X, Y, and Z. Okay, good. And maybe it means you make like a few fewer errors. Anyways, there's this thing called row-reduced echelon form that we'll go over. And so row-reduced echelon form, you're just using the matrix. And rather than doing back substitution, which personally I kind of maybe like, you actually reduce this matrix further by going back up and reducing, eliminating the value, the coefficient of a variable from each row. Okay, so it's pretty easy to do. At this stage, it's pretty easy to do. So what I'm going to do, I'm going to eliminate the Z coefficient from row 2, and I'm going to do it very conveniently using row 3, because there's zeros here. You're going to see. It's going to work great. Okay. So row 1, I'm going to leave it alone right now. Don't poke that bear. But to make this one, I'm going to take row 2 from up here, and I'm going to add row 3 to it. Maybe my matrix is just a little small. These little hooky things really keep the numbers from jumping out. There we are. Okay, so here we go. I'm going to make row 2 in this matrix by taking the row 2 and adding row 3 to it. So 0 plus 0 is 0. 1 plus 0 is 1. See how easy that is since I've got zeros there? Negative 1 plus 1 is 0. Negative 1 plus 3 is 2. And I'm just going to leave this bottom row alone. There we are. Okay. So far, here's what I know. Z is 3. Now, look at this. This tells me right away that Y is 2. Okay. Now, we're just going to do one more magical thing. That is, we're going to make the coefficients of the Z and Y disappear from row 1. Now, just a word of caution. My example here is just way too easy. You don't have to multiply a row by another row to make this work. So you might have to do some multiplication of a row in order to make these disappear. Like if this was a 2, for example, there would be a 2 here. I would have to multiply this by 2 and subtract. Fortunately, I don't have to do that, but you might have to do that. Okay. Now, what I want to do is I want to make this go away, and I'm going to use row 3 to do that. I want to make this go away, and I'm going to use row 2 to do that. And then we will have it in row-reduced echelon form. Okay, here we go. So I can do row 1 from down here, and I can subtract, I can subtract row 3, and I can add row 2. I'm going to do this all in one sweeping action. Okay. So, oh, maybe I shouldn't. No, I will. 1 minus 0 is 1. And 1 plus 0 is also 1. So that's a 1. So I did 2 things there at once. Okay. Now, -1 plus 0 is -1, so really the row 3 thing is a bit redundant. Okay, but I'm taking row 1 and I'm adding row 2. So -1 plus 1 is 0. Okay, once again, 1 plus 0 is just 1, but I am taking row 1. I'm also subtracting row 3. And so 1 minus 1 is 0. And so I have magically made the, well, it's not magic, y and z coefficients disappear. Sorry, maybe that was too many operations at the same time. We'll find out. Okay, now, row 1 minus row 3, so 2 minus 3 is -1, plus row 2, so plus 2 is 1. There we go. I'm not doing anything with the remaining rows. There's my final matrix, and this is in row-reduced echelon form. I have zeros in this little triangle. I have zeros in that little triangle. These 3 planes intersect at the coordinate 1, 2, and 3. So there we go. I've got row-reduced echelon form. It's just another form of the matrix that tells you where the intersection is, and I don't have to do back substitution. All right, just so you know how it works. Okay, now we're looking at weird cases of planes intersecting. Weird cases, and we're going to look at how to identify those cases, okay? So, let's do this one. Absolutely no intersection of the planes at all. They're all parallel, okay? So, you can actually spot this one right out of the gate. So this might be 1, 2, 3, 5. In other words, x plus 2y plus 3z equals 5. And then 1, 2, 3, 6. And then what about 2, 4, 6? 11. All right. These planes are parallel. And I can actually tell just by looking at the original equation or its representation in matrix form, I can actually see that the normals are all either the same. So this plane has a normal of 1, 2, 3, as does this one. So in other words, the 2 normals to those planes are parallel. The normals are parallel. That tells me the planes are parallel. This plane, it's just a scalar multiple of the normal is just a scalar multiple of the others. And so that means that all 3 normals are parallel. Okay? So in this case, I have absolutely no intersection. I don't have a point where they intersect. I don't have a line where they intersect. I can probably see it kind of trivially by looking at the matrix itself, and I can see all the normals are parallel. Okay, so either they're the same normal or they're a scalar multiple of one or the other. Okay. And what will happen when I go to reduce this matrix, okay, is I'm going to end up with something that looks like this at some point. So I happily reduce my matrix, and all at once I wind up with this 0, 0, 0 equals 1. In other words, what this is telling me is 0, z equals 1. And that is inconsistent. Okay, when I get that, there's no value of z where I multiply it by 0 and I get a 1. So when I reduce my matrix or solve my system of equations, I wind up with this inconsistent solution down here at the bottom, 0z equals 1. Can't happen. And so I know I've got a problem. I don't have an intersection. All right. All the normals are parallel. Okay. let's look at this scenario. So all three planes are intersecting, and all three planes are intersecting in a line. Okay, so there they all are. This set actually has a solution, and the solution is the line. Okay, this is what it's going to look like. So you've happily reduced your matrix. I'm not going to do it here because that would just be boring. So 1, 2, 3, -2, 0, 0. Yeah, let's do 1, 1, 5. And then we get to our bottom line, and we've done this reduction, and we get 0, 0, 0 equals 0. And so this is that situation where we've got a 0z equals 0. Is it true? Yeah, true all the time. 0z equals 0. 0x plus 0y plus 0z equals 0. Absolutely, it's true. So in this case, we have a solution, but the solution is not a single point. The solution in this case is actually a line. So to get to the solution of this, what we're going to do is we're going to pull that old trick where we come up with the parametric equation of the line. Okay? So what we would do is we would say, okay, well, z is going to be equal to t. And then we're going to take this and we're going to, this is normally y plus z equals 5. But we're setting z equal to t. So we're saying y plus t equals 5. And so y equals 5 minus t. So z is equal to t, y is equal to 5 minus t. And then the last step is to do the substitution into the x. So x plus 2 times 5 minus t plus 3 times t is going to be equal to -2. I just don't want to erase any of my planes. And I wind up with the parametric solution, which is a line for all three. Anything super weird about that? All right, there's a little test you can do. So you can test for this situation. The normals to these three planes are going to be coplanar. Okay, they're intersecting in a line. The normals to these three planes are going to be coplanar. And so we can test that for coplanarity a couple of ways, but the absolute simplest way is to do the dot cross product of the normals. Okay? So the cross product of these two normals is going to give you a normal that is perpendicular to those two. And the dot product of two perpendicular vectors is 0. That's right. Okay? So you can actually test that with the dot cross product and you'll wind up with a 0. Okay. Good so far? This one's my favorite, the pup tent solution, or the pup tent lack of solutions, okay? This one, you'll see, it's a really special case. Two planes will intersect in a line. So choose any two planes. The solution to that two-equation system is going to be a line. And we know how to find the solution to where two lines intersect, or sorry, two planes intersect. It's a line. It's that thing where you set z equal to t and then substitute it back and get y and x in terms of t. All right. If I did the dot cross product on this pup tent thing, same thing. I'd actually get a 0. Okay. So dot cross product here, doesn't matter what order you do, the dot cross product in. is also equal to 0. The way I'm going to detect this is when I'm reducing my matrix. So once again, this is going to be one of those cases where I get where I get down to here. So I reduce my matrix. All right, I've done a bunch of stuff up here. It's super boring to watch somebody to do at a blackboard. But I get down to here, I've got my bottom line. I'm all ready to figure out where the three planes intersect. And the solution is this 0, z equals 3. Okay, so this is going to give an inconsistent solution again. All right, 0, z equals 3. That's going to give an inconsistent solution. That's telling me those three planes do not intersect simultaneously at a location. Okay, two of them do. So these two, I could make a parametric equation to find out where they intersect, or these two, but all three of them don't intersect. Okay, so once again, this one is inconsistent. And you'll notice that none of the normals is a scalar multiple of another normal. Okay, last situation, which is, I don't know, I like that one. I like the way it looks. So this plane is parallel to this plane, and then there's a third plane cutting through. Same sort of situation, okay? We have a solution to this plane and this plane. We also have a solution to this plane and this plane. Either of those solutions is a line, which I could find a parametric solution to, but there is not a solution to this plane up here and this plane. They're parallel, they don't intersect. I'm not going to get a solution. So basically, in this case, you'll notice that the normal to this plane is going to be either equal to or some scalar multiple of the normal to that plane. Okay, so yeah, normals are scalar multiples. Okay. There's also the trivial situation where these two planes are actually the same plane. Okay, so that's it. That's the vectors portion of the course. And yeah, we're done in a very reasonable amount of time. So be able to recognize when you get those situations. So if you're reducing a system of equations or you're reducing a matrix, when you get down to that bottom line, it kind of tells you something about that system of planes, okay? Obviously, if it comes to a single point, you get a nice solution for z. If you get 0, z equals 0, well, you've got a situation where they might be a line, okay? In other words, anything works. And then you might get an inconsistent system, okay? If they're not all parallel, then you're going to be able to recognize the inconsistency based on the 0, z equals 12 thing. All right, that's it.